Chapter 2, Vectors and Phasors. So far, we have discovered that we can analyze AC currents and voltages using RMS values for resistive loads. That is to say, the AC currents and voltages are in phase. However, that is not always the case. So we have another dimension to deal with, and in doing that, we developed another tool. It's called a phasor. I'm sure you all have seen the difference between a scalar quantity, or something that's a magnitude, has no dimensions. Its length, area, volume, speed, mass, density, temperature, etc. And the difference between that and a vector, which has magnitude and direction. And some of the examples for a vector would be displacement, direction of velocity, acceleration, momentum, force, electric fields, magnetic fields, etc. Phasors have magnitude. They also have direction like a vector, but they have one more dimension, and that is phase angles, because the phasor is rotating about its tail, and when we do the analysis of different phasors, we take a snapshot or we stop the vector from rotating, and then we look at its phase angle with respect to the horizontal, or at times with respect to other vectors. Okay, so let's build that tool. How exactly can we represent AC quantities of voltage and current in the form of a vector? So we start by letting the length of the vector represent the magnitude or amplitude. That could be RMS value or peak value, as long as we maintain that same dimensional feature as we're doing the analysis. So if we start with RMS values, we stick with RMS values for the whole process. If we start with amplitude only, then we stick with amplitude only. The greater the amplitude of the waveform, the greater the length of its corresponding vector. And what we are looking at right now is the way a phasor represents or is related to a sinusoidal waveform. The vector, as you can see, is rotating about its tail, and it traces out the amplitude of the sine wave in the time domain. So let's just stop that for now, and let's do a little bit of analysis. We started out by saying that the vector or phasor has a magnitude A, and that is the peak magnitude of the phasor. And that could be either measured in RMS value or just peak or amplitude, as long as we maintain the same denomination as we are doing our analysis. In the time domain, where you see the graph of the AC quantity with respect to time, it goes from a positive A to a negative A, back through 0 to a positive A, back through 0 to a negative A. If we stop the rotation, as we have done here, the phasor forms an angle with the horizontal. And I'm going to call that angle omega t for now. It could be in degrees, it could be in radians. It doesn't matter as long as we maintain the same dimensional quantity. For now, let's assume that it is in degrees. So the phasor A forms an angle of so many degrees, which is equal to omega t. Omega is the frequency of the oscillation, whether it's in the time domain or it's a phasor, how fast the phasor is rotating. And the frequency, in this particular case, we're calling it degrees per second. It Could be radians per second, but in this example, we're going to just say it's degrees per second. T is in time, there is time, and it's in seconds. So omega t, if you take frequency in degrees per second and multiply it by time, that will give you a phase angle or an angle. And that's what's projected along the time domain axis. You can see omega t. So what it's tracing out there is the number of degrees over a period of time. If we wanted to measure the amplitude of that particular graph that's there, if we wanted to measure that, that's the same thing as writing it as A sine omega t. Now, omega t, remember, is an angle, and depending on where you are in time, that will give you a number anywhere between -1 and +1. Then multiplying it by the magnitude of the phasor gives you where you are on the vertical axis. So as that phasor rotates, the vertical displacement will be exactly A sine omega t. Now, the speed with which that phasor is rotating depends on, in a utility, how fast the frequency is rotating of the system. And in North America, that's 60 cycles a second. So it's greatly reduced in speed here, just so that you can see what's going on. If it was rotating at 60 times a second, you would just see a blur. You wouldn't see what was going on here. The thing to take away from this is one phasor only. If we added a second phasor to this system, and that phasor does not necessarily have to be in phase with the first phasor, you're going to get two graphs of sine waves. They both are going to have you're going to be equal to a function called a sine wave, which is A sine omega t. The thing to take away from here is omega is the same. In other words, the speed of the rotation of the phasors are identical. Doesn't matter whether you're measuring current, voltage, or other voltages in the system, all the phasors are rotating at the same frequency. And as I said, in North America, that's 60 times a second. Whether you have 1, 2, or even 3 phasors, they are rotating in the same direction and with the same angular velocity. And when we do our analysis, we usually just stop them from rotating and measure them with respect to each other, because it's not necessarily how fast they're rotating that we are interested in. We are interested in magnitude and phase angle. So we stop the system from rotating at some point, and then we do our analysis. So what you see here is two phasors. One could be current, one could be voltage, or they could both be voltages, or they both could be current. I'm not making that differentiation right now for this example. But what I'm doing is comparing the time domain with the phasor notation. And as we move the phasors closer together so that they are overlapping, now you will see these phasors, as they are referenced one to the other, you could say that A and B are in phase. And you can see that with the time domain graph. The one is right over top of the other. And not only are they in phase, but they are also the same value. In other words, the magnitudes are the same. And in phasor notation, it's one on top of the other. So there's zero phase shift between A and B. In this example, you can see that the phase angle of the red is straight down and the phase angle of the blue is from left to right. And you can see what has happened with the time domain graphs as well. In this case, we say because the rotation is counterclockwise, and that is a standard that we usually adopt in the analysis worldwide, the rotation is usually assumed in a counterclockwise direction. So we say that phasor B, the blue phase, leads phasor A, the red phase. And it's leading it in this case by 90 degrees. And you can see that in both the time domain as well as the phasor notation. The phase shift, we say, is 90 degrees. There's a 90-degree phase shift between the blue and the red. And in this case, the red will lead the blue. And it's going to be leading it again by 90 degrees. So the phase shift is 90 degrees. The greater the phase shift in degrees between the two waves form, the greater the phase angle difference between corresponding phasors. Being a relative measurement, like voltage, phase shift or phase angle only has meaning in the reference to some standard waveform or another phasor or vector. Generally, this reference waveform is a phasor along the horizontal axis, such as the blue phasor in this case, which would be a waveform starting at t equals 0 in the time domain. Sometimes this reference is just the x-axis of the rectangular coordinate plane. There are characteristics for the phasors which we have already discussed, and they can vary in length or in magnitude. They rotate with the same frequency. They are all still relative one to the other and the same distance unless the parameters of the circuit change. They are all rotating about their tail, and they all rotate in the same direction, and the standard direction we usually adopt is counterclockwise. There are a couple of ways of describing phasors in our system. One is polar notation, as I've indicated here. Polar notation is used in conjunction with what we call the polar plane. The phasor is denoted by the length, otherwise known as the magnitude, and the angle of the phasor, usually with respect to the horizontal, as it is in this case, and it's denoted by this symbol here that looks like an angle itself. For example, this particular vector, if it was going to be described, would have a magnitude of 8.4. Now, it doesn't matter whether that's inches or feet or miles, as long as you maintain this same dimensional quality. This is 8.4. And after the angle symbol, the angle is usually denoted with a small superscript 0 after the number. So this particular phasor notation is 8.4 at an angle of 32 degrees. Now, that phase angle can either be positive, and if it's greater than 270 degrees, as it is here, you can see that that is denoted by 8.4 at an angle of plus 312 degrees. But in polar notation, that angle can also be a negative angle, and it is the same phasor. The only thing is the angle measurement is negative in this case, minus 32 degrees. Here are for examples of what phasors might look like, and in the upper left-hand corner, you see that that phasor is 8.49 at 45 degrees. The phasor that you see in the upper right-hand corner can be denoted in two ways, either with a plus or a minus sign. It is still, the magnitude is the same, 8.06, but if you measure it in a negative angle, it's minus 29.74. In a plus value, it's 330.26 degrees. Same phasor, just two different descriptors. The one in the bottom left-hand corner, 5.39 at 158.2 degrees. And again, the one in the bottom right-hand corner has two ways that you can list it. One is the magnitude is both 7.81. The positive displacement or degree angle is 230.19 degrees, or minus 129.81 degrees. The other way of describing a vector can be done in rectangular notation. In rectangular notation, the phasor is taken to be the hypotenuse of a right angle triangle by the addition of lengths of the adjacent side that you see here in blue plus the opposite side, which is also designated in blue. Rather than describing the phasor's length and direction as it was in polar notation, we denote it with the how far right or left and how far up or down that phasor is. Those two dimensions are written in the form of two figures, the one on the left 4 and the one on the right plus J3. Now, the J in front of the 3 is not a variable. It is what is called the J operator. And the J operator will take a vector or a phasor and it'll rotate it through 90 degrees so that the previous phasor that you saw there, 3, is now pointing straight up and down, and it is plus J3. So there's a pair of numbers describing the vector in rectangular notation. The first one is the left or right designation, and in this case it's plus 4. The second one is the how far up or down, and in this case it's plus 3, but to denote the fact that it is going north and south, if you would, it is given the J operator so that it separates it from the number on the left. The number on the left, the left or right dimension, is known as the real number, or it's along the real axis, and the 3 is along what they call the imaginary axis, and that is denoted by a plus J going from 0 up, and it's a minus J as you go from 0 down. In the way of an example, this particular phasor, and we've just seen it before, is 4 plus J3, and it is in the first quadrant, and its both numbers are positive. If that phasor was in the second quadrant, as this example is, you would have a minus 4, but the distance along the J-axis is still positive, and so it would still be J3. And that is in the second quadrant of the rectangular notation. Another example would be this phasor, and it is in the minus J direction, but it's in the positive real axis direction, as all numbers in the fourth quadrant are. So the first number is going to be 4 plus 4. the second number is going to be minus J3. Now what we've done is we've just looked at two different ways of describing a phasor or a vector, if you would. And one was the polar notation and the other was the rectangular notation. You'll notice as I switched from one to the other, the phasor did not change. Its magnitude and direction remained the same regardless of whether you're in the polar coordinate or the rectangular notation. So you can convert one system to the other because the vector or phasor does not change. For example, I've written the phasor here and I've described it in both the rectangular form as well as the polar form. The rectangular description of this particular phasor, and it's the black arrow in this case, is in rectangular form it is +4 plus J3. In polar form it would be a magnitude of 5 and it would be at an angle 36.87. And by the way, you might recognize this is a 3-4-5 triangle. However, we're going to analyze how we can switch from one form to the other. Let's say we have the phasor written or described in polar form. In other words, we've been given that it's a magnitude of 5 at 36.87 degrees, and we would like to know what the rectangular dimensions are in the rectangular form. We would take the real component, and it's just taking the magnitude of 5, and you would multiply by the cosine of the angle, which is 36.87. And if you look that up or you calculated it with your smartphone, it would be equal to 4. And in the case of the imaginary component, the north-south component, you'd take the magnitude and you'd multiply by the sine of 36.87 degrees, and that would give you 3. So we successfully converted the polar form to the rectangular form. And if we were going in the other direction, in other words, if we were given the rectangular form of 4 plus J3 and we wanted the polar form, the first thing is the magnitude is just using the Pythagorean theorem, which says that the hypotenuse of a right angle triangle is given by finding the sum of the squares of the lengths of the other two sides, which is 4 squared plus 3 squared, which is equal to 5. So we know how to get the magnitude. The angle is just finding the arctan or the arctangent of 3 all over 4, which is equal to 36.87 degrees. So that is the other method of going in the other direction from rectangular form to polar form. If two AC voltages 90 degrees out of phase are added together by being connected in series, their voltage magnitudes do not directly add or subtract as with scalar voltages in DC. Instead, these voltage quantities or phasors must add up in a trigonometric fashion. A 6-volt source at 0 degrees added to an 8-volt source at 90 degrees results in 10 volts at a phase angle of 53.13 degrees. Vectors as well as phasors can be moved around in a plane as long as their direction and magnitudes are maintained. You add two vectors or phasors by placing the tail of one on the head of the other and then connecting the tail to the head of the result, just like you see in the picture. Compared to DC circuit analysis, this is very strange indeed. Note that it's possible to obtain voltmeter indications of 6 and 8 volts respectively across two AC voltage sources, yet only read 10 volts for a total voltage. We just went through the mathematics and came up with the fact that the resultant voltage was 10 volts at 53.13 degrees. We had to find the square root of the sum of the squares of two sides, and then we had to take the arctangent, which when you're adding two vectors together is a little bit tedious. However, if we had worked in the rectangular notation, we would have had 6 volts at J0 added to 0 plus J8, which we only have to add up the real sides and then the imaginary sides, and that, if we stayed in the rectangular notation, would have been the same result, only it was a lot easier to add two vectors together if they were in the rectangular notation. So that brings us to looking at how to work with phasors in arithmetic, if you would. So if you're adding phasors together, you simply add up the real components of the phasors to determine the real component of the sum, and you add up the imaginary component of the phasors to determine the imaginary component of the sum, as you see in this example. For example, the first one there, you have a phasor that is 2 plus J5 added to a phasor that's 4 minus J3. So if you add those two together, it's 4 plus 2 is 6 for the real component, and 5 minus 3 is the imaginary side, so that works out to plus 2 or plus J2. For the middle one, you have a phasor 175 minus J34 added to a phasor 80 minus J15. The real components add up to 255, and the imaginary components add up to minus J49. And the last one is a real component of minus 36 plus J10 added to a phasor 20 plus J82 results in minus 16 plus J92. It's very simple. It's just a matter of adding the two separate numbers together. If there are minus signs involved, that just automatically works into the process. When subtracting one phasor from the other, it's essentially the same process as addition. Only thing is we have to keep track of the operator or the minus sign. So I've placed the second phasor in brackets. In other words, the subtrahend of all of our three examples. I've placed the original phasor in brackets. So the first one on the left, I'm subtracting phasor 4 minus J3 from the phasor 2 plus J5. So when you do that, all you have to do is remove the brackets, move the minus sign inside the brackets, and the subtrahend, now the 4 will now change to a minus 4, and the minus J3 will change to a plus J3, and then you just add the two of them together. So subtracting 4 minus J3 from 2 plus J5, the real components add up to minus 2. The imaginary components add up to plus J8. And the second one, we have 175 minus J34. We're subtracting 80 minus J15 from that first phasor. So it's going to be 175 minus 80, which is 95, and minus J34 plus J15, resulting in minus J19. And finally, the last example we're subtracting 20 plus J82 from minus 36 plus J10, which results in minus 56 minus J72. Once we get into the analysis of complex circuitry using AC quantities, you're going to run into the requirement for multiplication and division as well. So when we're doing multiplication of phasors, the polar notation is favored to work with because it's very simple. All you have to do is you multiply the polar magnitudes together and you add the polar angles together. For example, we have two phasors here, A at B degrees multiplied by X at Y degrees. Then the answer is going to be A times X at an angle of B plus Y. So let's have a look at that in the form of an example. We have two phasors here, 35 at 65 degrees, 10 at minus 12 degrees. You multiply the 35 and 10, which gives you 350 for a multiplication of the magnitudes, and the angle is going to be 65 plus, and in this case, it's a minus 12 degrees, so it's actually 65 degrees minus 12 degrees, resulting in 53 degrees. Here we have two phasors being multiplied together, 124 at 250 degrees times 11 at 100 degrees gives us 1064 at minus 10 degrees, or 1364 at 350 degrees. And finally, you've got two phasors, 3 at 30 degrees and 5 at minus 30 degrees, results in 15 at 0 degrees. So it's a fairly simple process when you're multiplying. So really, if you're going to be doing mathematics or arithmetics, not using a calculator, which in this day and age we would, or a computer. However, what happens is when you're in the form of multiplication, you use polar notation. And when you're in adding and subtracting phasors, you do it with the rectangular notation. And you may have to flip back and forth to make your life a little bit easier, but that's how multiplication and addition or arithmetic works with phasors. Now, division is much the same as multiplication in that you're going to divide the magnitudes, one magnitude from the other, and you're going to subtract the angles. So in our generic example here, we have a phasor of A at B degrees divided by a phasor X at Y degrees. So it would be A divided by X would give you the magnitude of the division, and you would subtract Y degrees from B degrees to give you the resultant angle that you are looking for. So let's look at a couple of examples. 35 at 65 degrees divided by 10 at minus 12 degrees. You divide 35 by 10 is 3.5, and you are going to subtract minus 12 from 65. It's the same as adding 12 to 65, resulting in 77 degrees. In this example, you have a magnitude of 124 at 250 degrees being divided by a magnitude of 11 at 100 degrees. So 124 divided by 11 is 11.273, and you subtract 100 from 250, leaves you with 150 degrees. As a final example, you got 3 at 30 degrees divided by a phasor 5 at minus 30. So 3 divided by 5 is 0.6, and 30 minus 30 is actually 30 plus 30, which gives you 60 degrees. The reciprocal is just another form of division. So it's really, if you have 1 over the phasor 35 at 65 degrees, that's the same as a phasor 1 at 0 degrees. So again, you just divide 1 by 35 for 0.02857, and 0 degrees subtract 65 degrees is just minus 65 degrees. The second example, the reciprocal of 10 at minus 12 degrees is 1 over 10 at minus 12. Well, that's the same as 1 at 0 degrees over 10 at minus 12 degrees. And I'll let you just look at that. We don't have to repeat it all. And if you have a reciprocal of 1 over the phasor 0.0032 at 10 degrees, that's the same as 1 at 0 degrees all over 0.0032 at 10 degrees, results in 312.5 at minus 10 degrees. And this ends chapter 2.